All right, thank you very much. So it's so great to be back in Austin. I love this city. It's probably my favorite city. So just let's jump right into it. And actually, Raquel kind of previewed this. So some of you might be wondering why this is a sequel, right? So actually, it turns out about 4 years ago, I spoke at the very first Astronomy on Tap in Austin about the Rosetta Mission. Now, at that time, it was a lot earlier in the mission. It was only a few months in. The lander PHILAE had been set down to the surface. Actually, I should ask first, how many people have heard of the Rosetta Mission? Okay, good. So they've just sent the lander down. We weren't exactly sure what had happened to it. There were some ideas. So I figured, 4 years later, now the mission's over, should give a nice update and wrap up of what happened, actually. So first, let's actually start with a little introduction to comets and what they actually are. So comets are fairly small, astronomically speaking. They're about 1 to 10 kilometers across and consist of ice and dust, and they orbit around the sun. So when they're far away from the sun, this is all they are. So they're this kind of solid body of ice and dust, and we term this the nucleus. So this is an image of a comet called 103P Hartley 2 that was taken by the NASA EPOXY mission. That mission was about 8 years ago now. So you can kind of see here for scale, this is about a mile. So, big by human standards, small by astronomical standards, much smaller than the massive galaxies that were being talked about earlier. However, when these dusty and icy objects get close to the sun, those ices begin to sublimate, and you get the formation of a temporary atmosphere around the nucleus called the coma. And that also takes out gas and dust out into and forms this coma. And then, oops, did not want to do that. So this gas and dust then can interact with light from the sun and also particles from the sun and form these striking tails that they're often so famous for. All right, so I kind of mentioned that they're dust and ice, so let's quantify a little bit more exactly what they're made of. So kind of the canonical term is to call them dirty snowballs, though recent work is actually suggesting they're probably more like icy dirt balls, more ice than, or more dirt than ice, though that's still very much under debate in the cometary community. So that kind of translates down to, about 50 to 80% refractory material, which is just kind of a fancy way of saying rocky material, sandy material, stuff like that. So mostly that. But then what I work on is really the icy component. That's what I'm interested in. So this icy component is mostly water. So you can see in this pie chart, it's about 80% of the icy mass of the comet. And then you have carbon dioxide and carbon monoxide, and then a bunch of other trace species, things like methanol, ethane, methane, ammonia, hydrogen cyanide, stuff like that. It's a few percent of the volatile mass of the comet. All right, so I kind of mentioned that comets, the ice doesn't melt, it sublimates. So basically to describe sublimation, if you've ever seen dry ice, you've seen sublimation. So this is basically because this is frozen carbon dioxide ice, and basically at the Earth's surface, the atmospheric pressure is not enough to support the liquid phase of carbon dioxide. So it goes from the solid phase directly into the gas phase. And since comets are in the vacuum of space, that pretty much occurs for every ice on the surface. So even water doesn't exist in the liquid phase. It's a solid ice, it gets heated up, and then goes directly into the gas phase. And then that leads, again, to the formation of the coma and these beautiful tails that we often see. All right, so what kind of orbit? I mentioned they orbit around the sun. What kind of orbits do they have? So here's just kind of a few examples of comet orbits compared to the planets in the solar system. Now, the separation of the planets is not the scale here, but so you can see that the comets have lots of varying orbits. You have comets like Tempel 1 here, which only has about a 5.5-year orbit to go around the sun. Whereas you have other comets like Hyakutake, which appeared about 20 years ago, that has a 17,000-year orbit. So a very large range in orbits. And the other thing to really note is whereas the planets have these pretty much circular orbits, they're pretty much always the same distance from the sun, more or less. whereas the comets have these highly elliptical or eccentric orbits. And so they often will spend lots of time far, far away from the sun, and then they'll spend a very short period close to the sun where they get this intense heating and you get the sublimation and the formation of the coma and the tails and everything like that. Okay? So, it is. I guess it is. Woo! All right. Shout out to Pluto. All right. So that's the kind of orbits they have, but that's not, they didn't, when the solar system formed, that's not the orbits that they had. So where do they actually come from? So we believe that comets have kind of two main reservoirs. They come from the two structures called the Kuiper belt and the Oort cloud. So the Kuiper belt is where Pluto orbits, and it's just beyond the orbit of Neptune, so it's kind of this belt-like structure out there in the outer reaches of the solar system. So this is where we think a lot of those short period comets like Tempel 1 come from. However, the Oort cloud, but these other comets like Hyakutake, for instance, they come from this structure called the Oort cloud. And this is a nice spherical distribution of comets which stretches about a quarter of the way to the nearest star. So way out there. And this is where we think a lot of the long period comets come from. So you basically have these two main reservoirs. Now I will stress that they didn't necessarily form in these places, but that's kind of where they ended up after the chaos of the early solar system. All right, you're thinking probably, okay, that's all great, Adam, but why do we care? So why do we care about comets? So, as I kind of hinted at before, so they're basically leftovers from the formation of the solar system. So early in the solar system, you have the forming sun, and you have this disk of gas and dust that forms around the sun. And from that disk, you get the coalescence of all the planets and basically every object in the solar system that we know and love today. However, while as a planet like Earth has undergone a lot of changes in the 4.6 billion years since then, these comets have not. They've been stored way far away from the sun. They haven't been heated. Nothing's really changed much with them until they've been pushed back into the inner solar system. So we can kind of use them as fossils or time capsules to understand the early solar system, how you form volatiles and how you incorporate these objects into planetary bodies. So kind of an equivalency, if you see a comet, you can kind of think of dinosaur bones. They're kind of the same thing. All right, so because of this importance, they have often been a target of spacecraft missions. So pre-Rosetta, this is a sample of the 5 comets that we actually have images of their nuclei, so that's the solid part. And you can see there's a wide variety of sizes and shape, even in this very small sample of 5 comets that we have seen. So some are kind of more or less spherical, like Veal 2. Other ones have this kind of bilobate or even bowling pin structure, like Hartley 2 or Borrelly, and even Halley has hints of that. So a lot of variety, but the thing with all of these missions is they were only very short flybys of the nucleus, usually only lasting a few hours. So basically you just fly by the object, you take as many pictures as you can, and then you move on. And that gives you a nice snapshot and can give you a lot of good data, but it doesn't really give you a good picture of the long-term behavior of the comet. And that's when we get to Rosetta. So Rosetta is a mission that was led by the European Space Agency to a comet called 67P Churyumov-Gerasimenko. Gotten a lot of practice saying that name. And here's just kind of artist conception of, here's the main spacecraft, and then it had a lander called PHILAE, and that's just BB-8. Yeah. So the thing that was really groundbreaking, there was actually 2 aspects of the Rosetta mission that were really groundbreaking. So first, the Rosetta mission is an orbiter, not a flyby. So it spent over 2 years orbiting this comet and studying it, day after day after day. So you can really get a very complete map of the entire surface of the comet, which really hadn't been done before, and you can also see how the comet is changing over time. And the other aspect is this guy right here, Philae, the lander. This is the first time we'd ever attempted a landing on a comet. So 2 really groundbreaking aspects to this mission. All right, so here's this kind of GIF kind of showing the long journey that Rosetta had to get out there. So it was launched in 2004, and there are multiple gravity assists from the Earth. So it got to the Earth about a year later, gets a gravity boost that pumps it out a little bit farther, and kind of coming back in, and we get a Mars gravity assist in 2007. And then we're going to get another Earth gravity assist. And then back out again, a little bit farther this time. Flew by an asteroid, just for good measure. Coming back in, a third Earth gravity assist in 2009. And then now we're really starting to get out to the comet. We've gotten enough energy, fly by another asteroid, and it's trying to gain on the inside here. Entered deep space hibernation in 2011. And then a few years later, they were able to wake it up. It's coming up here. Yep, exited early in 2014. And it's getting very close to the comet now. A slight course adjustment to make sure it actually gets to the comet. Arrived at the comet in August of 2014. They have a bunch of mapping operations because they have to figure out actually where they want to put the lander. And then November 2014, they did the lander. All right. And that was the journey. And then it stayed there for an additional 2 years, orbiting the comet. All right, so here are some of the first images of the comet that were obtained in July of 2014. So you can already see in these very fuzzy images that it kind of has this weird structure where there's kind of like these really two distinct lobes of the object. And then, of course, the internet got a hold of these pictures and said, that looks like a rubber ducky. So henceforth, it became the rubber ducky comet. So, for instance, here you just color it yellow, and then it's clearly a rubber ducky. All right, and here's just kind of another thing. So you can clearly see the comet rotating. Comet, just like the Earth, it rotates around its spin axis. This one orbits in about 12.5 hours, so about twice as fast as the Earth. And it's just kind of cool to see it tumbling through space. All right, so then in early August, they got close enough where they could start taking some really nice pictures. So this is kind of one of the first really close-up missions or pictures. And you can see a lot of interesting geology on the surface here, lots of craters and pits and all sorts of structure here that the mission would study in more detail over the next 2 years. All right, so to kind of give you a sense of scale, so this is the size comparison. So here is the comet, and that's downtown Los Angeles. So again, big by human standards, small by astronomical standards. And then so these were not necessarily all in the initial months of the mission, but here just like a bunch of the literally thousands of close-up images that the mission took. So you can see cliffs and boulders and jets of material coming off the surface, all sorts of cool stuff. And also, like any cool hip young person, it took a selfie. All right, so on to PHILAE, the lander. So after it was orbiting a few months, in November, they were ready to send the lander down. And so this was the plan, is that you would release the lander from the spacecraft very slowly. So it actually would take 7 hours to descend down to the comet. And then a combination of harpoons, retro rockets, and ice screws would keep PHILAE actually attached to the surface. And yes, harpoons. And so, and the reason you need that is because a comet is very small, much smaller than the Earth, so the gravity is very low. So there was no guarantee that if you drop something even very slowly, that the gravity of the comet would actually be enough to keep it there. And so what we actually learned is that PHILAE and the abominable snowman from Rudolph the Red-Nosed Reindeer have something in common. They bounce. So what actually happened is the release and the descent went very well. It actually hit very close to where they wanted to actually put the lander. But the problem was the harpoons and the retro rockets never fired. So basically, it just kind of went down and just right back up. And it actually was kind of lucky, because sorry for the people in the back that might not be able to read this, that basically the rebound, it ascended at 15 inches per second, and the escape velocity is 19.7 inches per second. So it nearly reached the escape velocity from the comet, which means it never would have come down. So luckily, it dissipated just enough energy when it hit. So there was this one bounce, hung in the quote-unquote air for about 2 hours, and then hit a second time. It's possible it maybe even hit a third time, and then eventually came to rest in a different spot that than was originally intended. But it did successfully land on the comet. All right, so what kind of happened is, so it landed safely, but unfortunately, due to the bouncing, it kind of landed in a very bad orientation for kind of in a crevice, and the site didn't get a lot of sunlight, so the solar panels couldn't really charge the battery. So this really resulted in the mission being a lot shorter. So they had initial battery life for about 3 days, and they were able to run all that science that they were initially going to do. But then since they weren't getting enough energy from the solar panels, they had to shut it down and hoped for better illumination later in the orbit so that the solar panels could turn it back on. And there was the Rosetta orbiter was able to establish contact in about June of 2015, but it was a very weak signal, and unfortunately that couldn't trigger any additional science observations. And then shortly after that, it kind of went dark for good, and they never were able to hear from it again. Though, despite this the much shorter duration for the PHILAE lander, there still was a lot of good science that was done in those first few days after the lander, after the landing. And so there was a concerted effort in the last days of the mission to actually try to find the lander, both for closure and also it's actually kind of important to know exactly where the lander is for actually interpreting the measurements that it made. So you can see, kind of zoom in, and no, not BB-8, PHILAE. There's PHILAE. So you can see it, so it's right on the edge of this image, and then there's the PHILAE lander. So you can kind of see it sitting on its side, not in a very good orientation, not exactly the way you would plan it, but at least they were able to recover it and actually image it and kind of figure out where it was. All right, so kind of with the rest of the talk, I want to try to summarize at least some of what, in my biased opinion, are some of the key results from the Rosetta mission. Obviously, in a 50-minute talk, I can't talk about everything that the Rosetta mission has found, but I'll try to do a few highlights here. So one thing that they found is that these pits that are all over the surface are often the source also of these jets of material, of gas and dust that are coming off. So they suggested a model where you actually have icy material under the surface that kind of sublimates and is able to permeate up through the surface and go into space. And then this creates a cavity underneath, kind of like a cave. And then eventually this material can't support it under its own strength anymore, and it collapses, and you form this pit. And then you can get additional sublimation of ice from the walls of these pits. And that's a possible, the origin of all these jets that we see coming off of comets. All right, so they observed a lot of outbursts. So we kind of see this in comets that we observe from Earth. They often will change their brightness unpredictably, but on this scale, we were able to actually observe it, even on a smaller scale. So they'd just be observing the comet, and you see these jets, and boom, all of a sudden you just have a huge outgassing event, only lasting half an hour, and then it would just go right away again. And they observed lots of these throughout the 2-year mission. So really showing that cometary activity is not just this kind of steady state expelling material into space, but you get a lot of these small scale outbursts at the comet. So one of my favorite ones is this experiment called CONCERT. So it actually used the combination of both the orbiter and the lander. So in order for the lander and the orbiter to communicate, you have to have some kind of radio transmission that's going back and forth. And that's good for transmitting data, but you can also, if you plan the orbit right, and basically you put the comet in between the lander and the orbiter, you can actually use that radio wave to probe the interior structure of the comet. And what they were really able to find here is that comets, which had been suspected for some time but not really proven, is that comets are actually mostly empty space. They're about, so we quantify this using porosity, which is kind of a percent of the comet, which is empty space, and they found it's about 70% porosity. So really 70% empty space. But this is all occurs on very small scales. There's no huge voids inside the comet. It's just at very small scales, just on even micron scales, the particles just aren't very well packed together, and there's lots of empty space between them. And my favorite part of the mission is this instrument called Rosetta, which basically was able to collect gas from the coma and analyze it and figure out what gases were present. So this really revolutionized our understanding of what gases are actually present in a comet. So everything in this list was detected by Rosetta at this comet. So a wide variety of molecules, and glycine, which is an amino acid, an incredibly complex molecule. What kind of surprising was to see molecular oxygen. You got a bunch of other molecules here, and also, yes, there is alcohol. All right, so after an incredibly successful 2 years, it was time to end the mission. So basically, at NASA or ESA or really any space agency, the way we like to end a mission is by crashing it into the object. So basically, they did that. There was an orbit, and then they just do a collision maneuver, and then they sent it back down to the surface, and that's where so both PHILAE and Rosetta are now sitting on the surface of this comet. The good news is there are plans that we might go back. So there's a NASA mission called CESAR, the Comet Astrobiology Exploration Sample Return, and this has been selected as a finalist to be one of NASA's next missions. So basically what this will do is, again, now we had an orbiter and a lander, so now the next step is we want to bring a part of that comet back to Earth and be able to sample it in the laboratories at Earth. And that's what this mission will do. It will go, descend to the surface, grab a sample, and then bring it back to Earth. Though I wouldn't hold your breath, the sample return is probably going to occur in 2038. So don't hold your breath, but hopefully this mission will actually go and we'll actually get a sample of a comet to bring back to Earth. So if you've got nothing else from this talk, I hope you realize that comets are awesome. They are beautiful and enigmatic objects that can help us understand the formation of the solar system if we know how to look. Thank you.
All right, thank you. We have time for a few questions. Let me see. Let me start with this guy right here.
What kind of velocity range do you have for comets?
Okay, so the question is what kind of velocity range you have for comets. So it can vary widely depending on the exact kind of orbit it has, but usually they will orbit anywhere from tens to hundreds of kilometers per second. So very fast by terrestrial standards.
All right, how about right here up front?
So how much of the mass is lost when they pass close to the sun through the outgassing and tail?
Yeah, excellent question. So the question was how much of the mass of a comet is actually lost when a comet goes around the sun? So there have been some estimates of this, and usually it's something on the order of about 1% of the mass or something like that. But one of the interesting findings of the Rosetta mission, and it has been seen in some other flybys, but really been confirmed by Rosetta, is that we kind of used to think that basically all the material was lost once it goes off the surface, but there's a lot of evidence that you actually get some, especially those dust particles, do fall back on the surface in certain areas. So particularly, if I can maybe go back to, yeah, sure, like one of the images here, that basically in the southern, so basically there's a lot of outgassing from the southern hemisphere, and a lot of this dust then falls back on the northern hemisphere and has actually quenched some activity coming from that. It kind of buries the ice so it can't sublimate anymore. So that's kind of an interesting, one of the other interesting findings from Rosetta.
All right, time for one more question. How about you right there?
What's the porosity of beach sand?
The question is, what's the porosity of beach sand? And actually, I don't know that off the top of my head. I would guess that it's less than comets, because beach sand is pretty tightly packed. So there is some empty space there.
My question for you, from AoT ATX number 1 to now 47. How are we doing?
I think you're still doing great. Getting, filling the place every night and going strong.
We've grown a little bit, right?
Yeah.
All right, everyone, give it another round of applause for Dr. Comet.